Okay, so good afternoon. What I will do today is finish the discussion on the linear estimator. Actually, most of this derivation you will finish in the exercise, but I just want to say a few words about the results, and then we will start a new topic. So we were discussing the linear estimator. We have some observations, Ri, which come from some distribution P of R given a one-dimensional parameter theta. And we wish to construct an estimator, theta hat, which is linear in its structure. So it's some linear combination of the Ri, perhaps with some bias. So this goes from 1 to n, where n is the dimensionality of the input. And our goal is to minimize the mean square error, which is theta hat minus theta square, averaged, this is very important, averaged over two probability distributions. One is the probability of R given theta, but we're also averaging over P of theta. So we imagine that theta itself is drawn from some distribution, and the distribution of theta might affect how we end up constructing theta hat. Okay, so last week I derived the equation, the requirement in the optimization of E that the derivative of E with respect to B, the bias, is 0. And what I got is that B is equal to the average of theta minus the average of R transpose W, the scalar. And as I mentioned to you, a consequence of this is that the average of theta hat minus theta, again averaged over the same probability distributions, which can also be written as d integral d theta P of theta average of theta hat minus theta over P of R given theta. This is equal, under this condition, it's easy to see that this is equal to 0. So a way to interpret or to state this mathematical statement in words is that the average bias of this estimator averaged over the distribution of P of theta. Okay, here we have an average over P of theta and P of R given theta. So an average over P of theta of the bias is 0. Doesn't mean that the estimator is unbiased. It's unbiased on average. Usually it will be biased. Okay. Anyway, this is where we ended up last week. And the next step is to take the derivative with respect to the Wi's. It could be biased because this is not a requirement that this quantity itself for any theta is 0. It's just, this tells us that averaged over theta, this is 0. So for one particular theta, it might be biased in some direction. In another theta, it will be biased in the opposite direction. On average, it will be unbiased. And you should, one very important thing to remember is that typically, when we have a prior on theta, even in maximum likelihood estimator will be biased. The prior introduces a bias typically. For example, suppose that R would not depend at all on theta, that R would not be informative at all about theta. All this derivation still leads to some expression for the estimator. What will be the estimator in that case? If R doesn't depend at all on theta. What did you say? It's the estimator is a number. It receives R and it spits out a number. So what number will it spit out the best estimator in this sense if we can't use R at all to estimate it? Yes, exactly. It will give us, so in that case, you can see this from I mean, clearly the weights will be 0. I mean, there's no point in using R if R does not depend on theta. And then from this equation, you see that B will be equal to theta average, which is also, you can see this from here because it has to be unbiased on average. So because we have a prior on theta, we can generate some estimate for theta even if we don't have any information about theta, and this estimate will be the average of theta, okay? All right, let's continue with the weights. So we would like to require that dE to dWi is equal to 0. And here I will not write down the derivation on the whiteboard. You will do this at home. But I will write the answer. So the answer turns out to have this following structure. The best weight vector, W, is equal to the product of a matrix C. It's the inverse of a matrix that I will call C, and I will write down its elements in a moment, times a vector that I will call U, where U, the vector U, okay, let's call this W star. Hmm? Yeah, so you know what? You will do it if you wish in your notebook, and I will keep it this way. So UI is equal to the average of theta Ri minus the average of theta multiplied by the average of Ri. So what is this? This is the covariance between Ri and theta. Right? This is a vector. The ith element is a covariance between Ri and theta. And the matrix Cij, this all comes out from the minimization. Okay? Also has a very nice structure. It's the covariance matrix of the inputs. Okay. So note that if just in a very hypothetical situation, if this matrix, the covariance matrix of the inputs, would be a diagonal matrix, and let's just suppose for a moment that it's proportional to the unity matrix, so all the inputs have the same variance, and they are independent of each other. Let's just take a hypothetical situation like that. You see that we weigh more strongly, in our estimate of theta, we weigh more strongly those inputs that are more strongly correlated with theta. Right? Because then this would be an identity matrix times U, and U, Wi will be larger if Ri is more correlated with theta. So this makes sense. But you also see, just a moment, Oten. So you also see that in general, our choice of the W will depend also on the covariance matrix of the inputs. Okay? So it's more complicated. I'll talk about that in a moment. Good question. I'll address it explicitly. So usually Cij will not be a diagonal matrix, and you'll see why in a moment. Okay? Done?
Can you repeat your argument with the assumption you made?
Yeah, so just suppose for a moment that C would be a unity matrix or proportional to unity matrix, so all the inputs have the same variance, and they're independent of each other. Then you see that what we would choose with W is just weigh each input according to how much it is correlated with the theta. So an input which is completely uncorrelated with theta we ignore, and an input which is strongly correlated with theta we take more seriously. Okay? But because the neurons are also, the inputs are also correlated with each other, this complicates things more, and the correct answer is this one. Now we need to address Roten's question. Yes? I think so. I mean, I think that, yes, it is related to widening. So you can think about, good question. So you can think about what this equation means if you go switch to a basis in which the different elements, so replace the input R by some other vector, which is a linear transformation of R, and choose it such that all the elements will be uncorrelated with each other and have the same variance. This is whitening. After that, after you do that operation, the choice of W in that space will be weighing each of these transformed inputs according to how much it is correlated with theta. Good exercise for home for next week. Okay, Neta, please note. Okay, so now Autumn's question. Why am I even asking whether Cij is diagonal or not diagonal? We assume that the inputs are uncorrelated with each other, right? So does that mean that Cij is diagonal? Actually, good. Let's hear some thoughts about this. So I claim that no, it does not mean that Cij is diagonal, and I want to ask you why. Okay. Actually, I didn't say. Okay. Actually, I didn't make any assumptions, right? I didn't make any assumptions about the relationship between R and theta, and that all this is very general. But let's suppose for a moment that observations Ri, that this distribution is such that the different R's are drawn independently of each other. I claim that nevertheless, this matrix will not be diagonal. Yes? What do you mean the parameters? There's one parameter, theta. Okay, but exactly. So the point is the following. This we might assume, and in many cases we will assume, that the different elements of R conditioned on theta for a given theta are drawn independently of each other. But all the average that we're writing here are also an average over theta. And theta introduces correlations between the different inputs, because all of them depend on theta. Imagine, for example, that all the Ri's are monotonically increasing. Their average is monotonically increasing with theta. Then, of course, if one increases, the other one tends to increase as well. So there will be correlation between them.
So the average definition of Cij is not average over R, it's average over theta?
So all the average that I write, unless I'm stating otherwise, the averages are this kind of average. It's like averaging over phi of theta and then averaging over the distribution of R given theta. It's the overall distribution of R condition in general. I mean, taking into account all the sources of variability. So this is a very important point. That even if R, you could imagine even a situation where there is no stochasticity in R, that R is deterministically determined by theta. Still, the different Ri's will be correlated with each other, and this correlation is induced by theta. Okay? Yes?
Isn't that doesn't that hold for everything we develop? Always we have some kinds of observations, and they depend on some parameters.
Well, it depends on the situation that we discussed. For example, when we discussed the discriminators, then we didn't have a continuous parameter. We had the parameter that had just two choices. And yes, the probability distributions of the outputs dependent on this parameter. They better depend on it, because otherwise we can't use the observations to deduce the parameter. But we didn't, when we wrote averages, we typically then meant an average given that parameter. So you have to look carefully. This is a general statement. When you write averages, you have to think carefully, what do you mean by the average? Over what are you averaging? Okay. And in fact, when we discuss discrimination, I typically, on what I did on the whiteboard, I typically assume that the theta 1 and the theta 2 are drawn from equal probabilities. But of course, if they were not drawn from an equal probability, the optimal estimator, discriminator, as you are supposed to check in the home exercise, is different. It's affected by the fact that there is a probability over the parameter. Okay, so So Cij is in general not a diagonal matrix. And let me just write down what is the optimal average squared error. I think that we forgot to put this in the home exercise, but nevertheless, I will not do it here, and I recommend to just check this. It's not, if after you do everything, it's easy to check also what I would write out right now. So, but to do this, you should use the expression for the variance of the error that we wrote last week. And when you do all this and plug in the optimal W, you get that this is equal to the variance of theta minus U transpose C minus 1U. And what I would like to note about this expression is that the matrix C is positive definite, or also C minus 1. I will not show it right now. Later today I will show it in a different context, because we'll do something very similar in the context of supervised learning. So this is all this is therefore larger or equal to 0. And I would like to ask you why it makes sense that the error is always smaller than the variance of theta. Why is the error always smaller than the variance of theta? Because what? But okay, how does this variance of theta is the parameter? I don't see why this is related. Theta is the variance of theta is actually the variance of the prior on theta, the distribution from which theta is drawn. So it's completely unrelated to the neural response. Was some other suggestion?
Even if you know theta, your best guess will always be after the variance.
Wait, if I know theta, my best guess would be to say theta, right? But what do you mean? If you
know the probability.
Okay, if I know the probability, okay, good. If I know the probability distribution of theta, we assume that we are optimized. We know the probability distribution. If I don't use anything, I can always just pick some number, right? And I can pick and the best choice will be to pick the average of theta in order to minimize this. And then my squared error will be simply the variance of theta. So even if I don't use at all the r's, I can always get an error which is variance of theta, but using the r's, I can improve it. Okay? So this is why the second term has to be positive, better be positive, and it is positive. And at home, you will also, so you will derive all these things at home, and you will also consider an example more specific, which is Poisson neurons. So the assumption then will be that each Ri is a Poisson variable with a mean that depends on theta, and they are independent of each other. And then the goal of the exercise will be to see what is the form of the Ui and what is the form of Cij under this condition. Okay, so I'm happy to announce that we. Yes. Yes.
When we try to find the B optimal and W optimal, why we cannot do it the opposite way? Why we cannot find W at the beginning and then B?
No problem. We actually need to solve both. You can see here that when I wrote the B optimal, it still depends on my choice of W.
And the same way.
And the same. So these were really coupled equations that you need to solve together.
So you need to plug in B in order to find the
Yes, yes, yes. And you can do, but when you start doing it, you can do it in any order you wish. Okay, so now I'm happy to announce that we finished our discussion on decoding. And the next topic which will occupy us until the end of the semester is supervised learning. So, okay, wait, I'll just erase the whiteboard first. Okay, so in general, when people talk about supervised learning, we talk about a situation where we want to learn to perform some operation or to do some computation where there are inputs and there are outputs, and we are told, we learn from examples. So we are given examples of inputs, and we're given it, for these examples, we are told what is the correct answer. Sometimes it might be a little bit more weak. We might be told a little bit less than that, but usually we imagine that we are told what is the correct answer, and our goal is to learn the relationship between the inputs and the outputs and be able to reproduce it, and maybe also generalize it to cases where the inputs are different from the examples that we've seen. Now, we are interested in supervised learning in the context of neural networks. And we imagine that we have a neural network. So this is a very general statement, but now I will describe a somewhat more concrete setup, which will really occupy us until the end of the course. So we imagine that we have a neural network. Okay, I don't know exactly how it's structured. It might be very complicated, although we will discuss very simple networks, which are feed-forward networks. We will not discuss networks that are recurrent like this. But just for the sake of the drawing, we imagine that these networks receive some inputs, x1, x2, xn, and that it generates some output that I will call y. I will assume that for now that it's one-dimensional, so there is one output. And the parameters are some weights in the network. They might be weights that connect neurons in the network, although initially we will not discuss the situation. And these might be the weights that connect the inputs to the network. So there are some synaptic weights. And our goal, is this still okay? No? And our goal is to approximate some function, some scalar function of the inputs. What do I mean by that? I'll explain in a moment. Okay, so we want our network to produce a y which is close to f of x. And in the context of supervised learning, we imagine that we are shown some examples. These will be some vectors x mu and some output, desired outputs, which are the value of the function f for the inputs x mu. And our goal is to adjust the weights w such that y of, so the output of the network, I can write it as a function of the input and as a function of the weights. And I want this output for each one of the examples by the way, mu goes from 1 to p. P is the number of examples. And my goal is that the output of the network to each one of the y mu will be close to f of x to y mu. What do I mean by close? We'll have to discuss this. This depends on the situation. No, so y is a scalar, but there's a different desired value of y for each one of the examples. Ah, thank you. And by the way, the y can be different things. It can be a real number. It might be a binary output. Okay, so we'll discuss both cases. Today we'll discuss a situation where the y is a real number, and maybe tomorrow, if we have class, or next week, we'll discuss a situation where the desired output is just a decision. It's a binary variable. And of course, in these two different conditions, our choice of how to define similarity of the answer will be different. But in general, this will be the situation. And so we want this to be true for all mu. But what we really often want when we talk about learning is not just to be able to fit correctly the answers for the examples that we were shown. We want our network to approximate correctly this function also for x's that are not one of the examples that we've seen. So this is called generalization. We will often ask, how well will this network do after we adjust it to produce correctly, or at least approximately, to the answers for the examples? How well will it do on other examples? And there are many variations on this general theme. As I mentioned, maybe I'll write this down. Variations on this theme. First of all, the nature of the variable, continuous, discrete. Also dimensionality. I mean, I will discuss mostly a case where, as I mentioned, where y is one-dimensional, but y could be also multidimensional. How do we measure the error? What is our choice of the error? How do we do the learning? How do we try to fit the weights such that they will achieve this goal? So, type of learning. And very importantly, the complexity of the network, or the structure of the network that we assume. We might have a very complicated network with many weights, or we might have a more simple network. We might feed forward, recurrent. We might have many weights, few weights. And we want to understand how the learning and also how the ability of the network to generalize depends on various parameters of the problem: the structure of the network, the number of examples that we've shown, the probability distribution from which the x's are drawn. This is also important. Okay, so this is kind of just a general introduction to what we want to do. And what I will do next is start by discussing the network with the most simple structure that we can think of. And this is a linear network. So we imagine that our inputs are x1 to xn, okay, and we have one output unit which generates an output y. So this is really not a network. It's one neuron, if you want, if you wish. It's one neuron that receives all the inputs. It weighs them linearly, and it generates an output, which is some wi xi. And I can write this also as w transpose x. Okay. I could have introduced also a bias term here, that y will be the sum wi xi plus b, as we did in the linear estimator. I'm not doing it just to simplify the algebra. Doesn't matter that much, and I will actually mention to you how things will change if we had a bias. Okay, so this is what the network computes. Given any input, and for a particular choice of weights, this is what the network will compute. And our goal is to learn some relationship y equals f of x, which is some scalar function. And we will learn from examples. The examples will be x mu, y mu, where mu goes from 1 to p. I should have written already that x, the input x, belongs to R to the n, small n. And now, since I already declared or decided that my output is a real number, I can decide on some criterion of how well we're doing in this learning. And my criterion will be, or my measure of error will be the mean square error. Of course, any choice of criterion for how well we're doing, we want it to be, or a measure of error, we want it to choose it such that the error increases if y mu, if y of x mu is, the further y of x mu is from y mu, we want the error to increase, and what I will choose is a square error. So let's call it epsilon of x, and it depends also on the weights. This is defined to be half y of x and w minus f of x. So for any, given the weights for any value of x, I can ask how I use this measure to quantify how well the network is reproducing the function. This is squared, and I want this to be small.
Why you put the half?
Why do I put what?
The half.
Oh, the half is just for convenience. Of course, it's completely arbitrary, but it's just for convenience.
We know x and we know w, and we're looking for
So,
f.
well, so we know f. I mean, okay, what do you mean by we know? There is some function f. When we construct the network, when we try to optimize the weights, we don't know this function. We are only shown some examples. And in these examples, we are told what is x and what is the corresponding y. So I didn't write it. Y mu is the true value of x for x mu here. Okay. We're shown these examples, and we try to adjust the weights in order to get good agreement. And a good agreement, we will decide to quantify how well we're doing by this difference squared. So using this measure of the error and given a training set, we can now construct a cost function for W that will tell us how well we're doing on a training set. So let's call this E training. E training will be simply the sum of epsilon of x mu W for all the mu's. Or in other words, it's equal to 1 over 2. Okay, it will be the average over all the examples. So it will be equal to 1 over 2p y of x mu W minus f of x mu squared. And there is a sum here. Sum over mu. Okay, so this is the training error. And so our strategy now will be to simply minimize the training error given all the examples that we've seen. So our goal is to make the errors as small as possible over the training set. And now we need to do the math. We need to figure out what this tells us about how we need to choose W. Okay? All right. So in order to do this, what we need to do is write down the training error as a function of the W's. But remember that y of x mu W is a linear function, right? This is y. Right? So what kind of function of W? We want now to optimize over W, right? All this we know the examples. We know x mu. We know f of x mu. We're viewing all this as a function of the W's, and we want to minimize it as a function of the W's. What kind of function of the W's is this? Yes, Maga? Quadratic. It's a quadratic function. Why is it a quadratic function? Because here we have something which is a linear in the W's, right? For each mu, y of x mu W is some sum over the W's. We then also have a sum over mu, but this is still some sum over the W's. We add to it some numbers, and then we square it. It's going to be a quadratic function of the W's. Let's see this. Let's write it a little bit more explicitly. I will actually not do the algebra. I will leave it either to the TA session or for you as an exercise. In general, any quadratic function can be written as a quadratic term, a linear term, and a constant term. So the quadratic term will have the form. Now this is quadratic in a multidimensional variable. W is multidimensional. So a general quadratic term in the W's has the form half W transpose C training. I will write down explicitly what this is in a moment. W. So this is a quadratic term if we expand this expression, and it will come from plugging in. Right? We would need to plug in here sum over Wi xi, and then we need to open up this square. So we'll get something like this. There will be a linear term that I will write. Any linear term can be written in this form, but I will need to tell you exactly what is this vector u. And there will be a scalar term that I will call a. Okay, so far I didn't do anything. I just rewrote this expression as a general quadratic form over the W's, but by writing down explicitly what we have here and opening up everything, we can find what is C transpose, what is U transpose, and what is A, and I will write down the answer. So I will do this here. So C training, TR stands for training set. C, the matrix C, has the following form. The ijth element is equal to 1 over P sum over mu, sum over all the examples, xi mu, xj mu. So this is a matrix, and this is the correlation matrix of the inputs, right? The vector u, the ith element of it, is equal to 1 over P sum over mu going from 1 to P y0 mu xi mu. So you can think about this as the correlation between the between f of xi and xi. Sorry? Because at some point I called it y0 and then I decided to not to use the y. Okay, not to use the 0. So there's no 0. Note that this is kind of an empirical correlation. I mean, giving over the examples that we were shown, this is the correlation between the inputs. And over the examples that we were shown, this is the correlation between the ith element of the input and the output. Yes, true. F of x, and I could also, and this is also y mu, same. Okay. And yes.
This is basically sufficient, right? If we have this, we don't even need to see the actual examples.
That's right. If we know this, we use the example. In a sense, that's right. I mean, to calculate the optimal W, you only need to know these matrices in vector. And just for completeness, I will also write the constant A. We don't really care about the constant A because we wish to optimize over W, and A doesn't depend on W. This term doesn't depend on W, but again, just for completeness, A is equal to 1 over 2P sum over mu going to from 1 to P y mu squared. Okay. Now, before we continue, I need to discuss a little bit the properties of this matrix. Actually, let's see what time it is. Okay, let's take a break and we'll do it after the break. התפלגות פרסונית, אבל עם איזשהו ממוצע שתלוי שואל על שאלה בגלקסי יש לך כזה? אוקיי, לא, אבל לכולם יש אותה למדה. לא, זה שהם אינדפנדנט זה לא אומר שלכולם יש את אותה למדה. לכל אחד יכול להיות איזשהו למדה אחר. למדות אחרות. אבל האינדפנדנט זה אומר מספר הספייקים של נוירון
הקשר בין הרזולוציה של L ומה קורה עם N.
כן.
כאילו, אני ניסיתי, אני לא יודע ממש מה כיוון צריך ללכת, אני ניסיתי ללכת עם... כי אני לא ממש... אין לי likelihood function ממש, כי אין פה. אני ניסיתי ללכת עם הכיוון, אם אתה אומר יש לנו אופטימל, אמרתי אופטימל unbiased, אוקיי, אז אמרתי, אוקיי, אז אני אנסה אולי עם קריימר ארבנד, אני לא יודע אם זה הכיוון בכלל. זה הכיוון? כי אני לא יודע, אוקיי.
זה הכיוון, אתה רק שואל על הסקיילינג, איך זה מתנהג בפונקציה שלהם.
אז זהו, כי אני יודע שאם יש לי אופטימל unbiased, אז אני מסיק את הקריימר ארבנד.
הגבול של n גדול.
אז זהו, אני לא יודע מה להגיד עם n קטן, אבל גם כדי לחשב את J הזה, אני צריך להגיד את
אני לא מבקש שתחשב אותו, אני רק מבקש שתגיד מה הסקיילינג, איך זה מתנהג בפונקציה של n.
מה קורה?
לא יודע, טוב, צריך לראות איפה התלות ב-L שם,
אני לא שאלה שדורש לך להגיע לעשות איזה חישוב מפורט.
אני לא רואה איפה התלות ב-L.
אוקיי, אז תחשוב על זה.
טוב.
אוקיי, אז
ה-F מייצג את המשוואות?
ה-F מייצג את התשובה הנכונה, לא. כאן ה-Y זה האוטפוט של הרון. Y זה האוטפוט של הרון, זה תלוי ב-X שזה בצורה לינארית. X זה מה שאני רוצה להשיג, שיכול להיות פונקציה לא לינארית. ה-Y mu זה...
אתה מניח שאתה בטוח יכול למצוא את התשובה הנכונה.
אוקיי, אז אתה יודע מה, בואו נשנה את זה.
כן, זה לא ברור רגע מי האמיתי, כי...
אוקיי, אני אגיד את זה, אני אחזור על זה בכלל.
אתה משלם Y mu, אני לא מבין מי האמיתי ומי כאילו אנחנו...
בגלל זה מה ששאלו אותי, היה לי בצע Y0. ואחרי התחלתי לוותר על זה, אני חושב שזה Y0 היה אמור להיות כאילו הערך הרצוי ברמת Y שהוא הערך
בכל מקרה, כרגע זה לא ברור מי זה.
כן, כי אתה ממש מודד אחד, ואחד יכול למדוד. אני אסתכל, והשני זה הערכה שלך מה חשתה שמורה על תוצאה בעצם.
יש גם טסט חוץ מהטריינים? לבדוק את זה?
אני לא אדבר על זה במפורש, אבל אני אדבר על generalization היום, שזה מבוצע על כל הערכים האפשריים שלהם.
מה יש לך פה? וקטור משין כזה?
פורט וקטור משין זה דוגמה לבעיה כזאת שבה ההחלטה היא בינארית, וגם הוא פשוטה למידה קצת.
כי בניסוי מה שעושים נגיד, לוקחים הזמן לדגימות, ואז לוקחים חצי מהדגימות, ואז לוקחים חוק כזה, ואז בודקים את זה על החצי של הדגימות.
זה מה שנקרא validation, cross validation.
זה זה?
כן. מה שאתה זה.
אפשר לשאול אותך שאלה של אינטואיציה, של השאלה השנייה, estimate all parameters. אני פשוט מסתכל על מה שאתה נתת, אני יכול לעשות את זה מתמטית, אבל אני לא מבין מה זה אומר לי ולמה זה נכון. למה אני יכול לקחת של תטא A, הווריאנס של תטא A, גדול מ-JII מינוס 1.
בשביל זה צריך לעבור על ההוכחה של הקריימר ארבנד. אני לא עשיתי אותה בשיעור. אתה לוקח את עיבוד מידה ולמידה. עכשיו
למדנו, אבל...
למדתם מידה רב-ממדי או רק למידה?
לא ממש.
לא ממש.
אז צריך להסתכל על ההוכחה על המקרה הרב-ממדי. שיש הכללה של ההוכחה על המקרה הרב-ממדי.
כי במקרה הזה אני מבין שזה ברב-ממדי, אבל במקרה הזה...
הנקודה החשובה היא שמה שכתבתי על הקריימר ארבנד, המשפט שכתבתי על הקריימר ארבנד ברב-ממדי, מתייחס למצב שבו אתה צריך להעריך את כל הרכיבים של טבע. אתה לא יודע אף אחד מהם, האסטימטור מקבל את ה-observations והוא צריך לתת את הערכה לוקטור. וכל אחד מהרכיבים הוא unbiased. אז זה המצב שאנחנו מדברים עליו כאן. אני מדבר על מצב אחר, מצב שונה, אבל זה בעצם הופך להיות חד-ממדי. אני מספר לך מה עם כל הפישות, צריך לבנות אסטימטור שרק יהיה איזה אחד מהם.
אז עכשיו מה האינטואיציה שזה נכון? זאת אומרת, אני יכול להוכיח את זה מתמטית, אבל...
לא, אז זה מה שתחשוב.
של האינטואיציה.
למה זה הגיוני באמת שהווריאנס של האסטימטור זה הוא בסדר בווריאנס?
אוקיי. אני אלך להתחלה, מה זה אומר וריאנס של האסטימטור?
זה אומר השביעה בריבוע שלו, נכון? זה לך הרבה פעמים שאתה... האסטימטור הוא unbiased, מומחים שהוא unbiased, אבל נותן את התשובה הנכונה, אבל יש לה איזשהו ספרד. סברותי, כי הארים הם מסתובבים.
אז השביעה בריבוע.
יודע משהו, אוקיי, אז אתה מספר לי שאני הגעתי לזה אתמול, וקיבלתי את זה, וגיליתי שאוקיי, זה נורא מפורסמים, אז מה שאני יודע זה שלכל אחד איזשהו יש למדה משלו, נראה לי שהתופעות שלהם, כל אחד זה למדה.
כל אחד מזה פונקציה, כל אחד מזה למדה זה פונקציה של תטא, יש למדה I של תטא. אוקיי, ואני רוצה תכתוב את ה... הרי אני מזכיר לך שהממוצעים האלה ממוצעים גם על תטא וגם על הגיבן. לכן צריך טיפה לחשוב וגם לכתוב על זה וריאנט.
כי גם מה שכתבת עכשיו עם השיר שלך שזה קצת, נגיד, כתבת איזשהו ביטוי, פחות משהו חיובי, נכון? זה מספר, נכון? התטא הזה זה מספר. עכשיו, זה וקטור, וזה וקטור, וזה איזשהו גם מספר. אז אני לא מבין למה... עכשיו אם יש לך איזושהי התפלגות אחידה של האסטימטריה, אין לך מושג, יש התפלגות נגיד מ-0 עד איזשהו x, בגובה 1 חלקי x, אז למה כאילו שתבחר בממוצע את האמצע?
כי זה מקטין, כי אתה רוצה להקטין את השגיאה, תחשוב שהיית... אוקיי, תחשוב ש...
כולם באותה הסתברות, כל ערך.
בסדר, אני אענה לך על השאלה. בוא נניח שתטא הוא מתפלג אחיד בין תטא 1 ותטא 1. אחיד. עכשיו תחשוב על סיטואציה שבה אתה לא יודע, האינפוט, התשובה שבכלל לא תלוי בתטא, בכלל לא אינפורמטיבי. עדיין מעצם העובדה שאני רוצה שתטא פחות תטא, אז ברור שאני יכול, אין לי שום סיבה להתייחס לאינפוטים ואני אתן פשוט איזושהי תשובה אחת. אז אני אקרא לתטא 0. עכשיו אני רוצה לבחור את תטא 0, ככה שבממוצע תטא 0 פחות תטא בריבוע יהיה כמה שיותר קטן.
זה
מוזר, נכון?
זה כמו שאתה ראית. אני זורק קובייה, מה אתה רוצה לנחש? אתה אומר לי תנחש 3.
זה קשור לקריטריון הזה של השגיאה בריבוע. זו נקודה מאוד חשובה, כשאתה רוצה לעשות מינימיזציה של שגיאה בריבוע, הפרייר של תטא משפיע על מה אתה תרצה לעשות. גם אם אתה לא היית יודע כלום על תטא מתוך האובזרבציות, כדאי לך לבחור את ה...
בגלל הפרייר.
כן.
לא, בקובייה זה לא, בקובייה אין.
נכון, כי אם אתה תבחר תטא 0 להיות ככה, אתה יכול לעשות את החשבון, בממוצע המרחק שלו מתטא יהיה הכי קטן,
ואם הפרייר הוא גם אחידה?
אני אומר, אם הפרייר הוא התפלגות אחידה, אתה תרצה לבחור את תטא 0 בדיוק באמצע ההתפלגות. עכשיו, אם זה התפלגות אחידה על כל הישר, אין לך השגיאה שלך תהיה אינסופית. במקרה שהאובזרבציה זאת בתטא.
זה נכון להקביל את זה לזה שאתה אומר לי, אני זורק קובייה, אני רוצה לדעת מה הערכה לפי...
אז תראה, אם היית...
אתה אומר לי תבחר 3, אל תבחר.
תראה, אילו הקריטריון שלך לקובייה זה בכלל משהו דיסקרטי. 1, 2, 3, 4, 5.
קובייה רציפה.
בוא דווקא נדבר על קובייה לא. 1, 2, 3, 4, 5. אם קריטריון השגיאה שהיה, מה הסיכוי שאני נותן תשובה נכונה? זאת אומרת, אכפת לי רק אם אני נותן לך בדיוק את התשובה לאיזה תאה או קובייה.
או כמה... כן, זה טוב לממוצע.
אז בכלל לא משנה, ברור שבכלל לא משנה מה אני אבחר. אבל אם אני אומר לך שאני רוצה שהשגיאה בריבוע כמספר, אז יהיה כדאי לבחור 3.5.
כן, אני רוצה שקובייה 3.5. אני לבחור 3 או 4 כל פעם. טוב לממוצע. אוקיי. ובקשר לא לזה, בקשר ל... עשיתי איזשהו סרט והסתכלתי על הדיקודר שלי. אני יכול להגיד שהוא לא נותן את המיקום טוב.
לא, אני רק רציתי לראות מה השעה.
אני לא חושב שהוא... אני משווה, הוא לא...
תלוי מספר הנוירונים כמובן. זה תלוי גם...
אבל הוא לא ייתן את המיקום טוב, כי הוא פתאום קופץ לי.
אני אגיד לך במה זה מאוד תלוי.
אם אני עושה סרט, אני יכול להראות לך, אם אני עושה סרט, אז אני רואה בהתחלה הסתברות סביב איזשהו ככה עיגול, ואז זה ככה עיגול, וצריכים עוד עיגולים.
אתה קודם תחת במצב שהמיקום זז, נכון? שהמיקום האמיתי זז.
כן.
עכשיו, קודם כל תתחיל לבדוק מה קורה כשהמיקום לא זז. מה קורה כשהמיקום לא זז? כי אז אתה מצפה שככל שיש לך יותר נוירונים, יותר אובזרבציות, יותר ספייקים. כן. וגם אתה מניח שעומד במקום. אם הוא עומד במקום, ברור שככל שיש לך יותר ספייקים, הערכה שלך למיקום תלך גם אם אתה תתחיל אותה מפרייר חלק לזה. תתחיל לא מפרייר שאתה יודע. אז ככל שאתה יעבור יותר זמן, הערכה שלך למיקום תהיה יותר ויותר טובה. א', תבדוק את זה. דבר שני, מה שאתה יכול ללמוד מזה, זה שזה משנה באיזה מהירות
יהיה לך יותר קל לעקוב אחרי המיפוי. אוקיי, אז תתחיל בזה שתעשה את מקדם הדיפוזיה מספיק קטן.
לא, אבל לוקח זמנים, מה שחשוב זה היחס בין הדגימה שלי למהירות שלי.
מה חשוב?
אם אני דוגם הרבה יותר פעמים זה...
אוקיי, אבל גם לחלוטין, זה יכול שקצב הספייקים יותר גבוה, לחלוטין זה יכול שקצב התנועה יהיה יותר גבוה. התנועה היא יותר איטית, אז אתה יותר להתקרב במצב של מעבר משמעות. ואז אתה מספיק לצבור יותר ספייקינג כשהוא במיקום מסוים, ואז אתה...
כאילו על הגריד של חלק מהנוירונים.
כן.
חלק מהנוירונים.
והוא נשאר במקום, אבל הנוירונים האלה זה מחסר יותר ספייקינג שמאפשרים לך לצמצם את הערכה, עד שהוא יספיק לזוז. אז תמיד בקיצור, העובדה אם זה עוקב טוב או לא טוב, זה היה בפרמטרים. חקר בפרמטרים ככה שכן יעקב טוב. עכשיו נראה לי שנטע רוצה להגיד משהו, אז...
אפשר לשאול גם עוד שאלה אחת שקשורה לפיזיקה שסתם חוצה אליה, זה משהו נכון מוזר, הנה גם אולי זה נכון מה זה טמפרטורה? כי נהייתי שוב מתעסקים. אני לא יודע, זה מה שלמדנו בכל זאת.
לא, טמפרטורה זה הנגזרת של האנטרופיה לפי ה...
אם אתה מודד את הטמפרטורה בכלל אתה מקבל איזשהו מספר. מה...
יש קשר בין, אם זה גז אידיאלי, אז האנרגיה הקינטית של המולקולות היא פרופורציונלית לטמפרטורה. זה בגז אידיאלי.
זה אומר שמה שדינמי זה המהירות של החלקיקים. המהירות של החלקיקים הולכת כמו הטמפרטורה פחות או יותר.
לא, כמו שורש טמפרטורה.
בסדר. השניהם במונט, בגז אידיאלי, נכון?
כן.
אז סתם, לא יודע, אולי זה חלום נכון, אבל איך זה יכול להיות שיש רוח קפואה? יש חלקיקים שנעים מאוד מאוד מהר, אבל קפוא כאילו...
כי אתה נמצא בטמפרטורה יותר גבוהה מהסביבה. הגוף שלך נמצא בטמפרטורה יותר גבוהה מהסביבה. מה שהרוח עושה זה שהיא... בעצם מה שקורה זה כשאין רוח, אז אתה יוצר איזה מין שיט, מגיע למצב שיווי משקל עם האוויר מסביבך. האוויר מסביבך הוא יותר חם מהאוויר שרחוק ממך. כי הרוח כל הזמן מסלק את האוויר היותר חם הזה וגורמת לך להעביר יותר חום לסביבה. אתה מעביר חום יותר מהר.
פשוט נראה לי כל פשוט, אני יכול לעמוד במקום שיהיה רותח מסביב, ובלי רוח, אבל כאילו אני מפרש רוח כמו, אתה יודע, האוויר זז יותר מהר.
אני אומר, מה שקורה זה שהרוח גם... טוב, אנחנו נדבר על זה קצת יותר...
כן, לא, זה סתם. זה סתם נראה לי לא הגיוני, מה שלמדנו.
הייתה הצעה, שהם כולם היו לחצי בית מחר בהצעה, שמראש נוציא כמה מילים מהפרוצדורה,
לדעתי יש סיכוי לא רע שגם הלימודים רשמית יסתיימו לפני.
לא, אבל אתה לא צריך לסיים.
לא, אני בעד.
כאילו שבכל מקרה נקבע ששבוע...
בואו נגיד ככה, שקודם כל נקבע בכל מקרה שהמתחיל מחר לא יתקיים תרגול באחר. לגבי השיעור נחליט לפי המצב. לפי החלטה רשמית שלנו.
מחר נקבע שבכל מקרה לא עושים ונעשה להם 2 שבוע הבא, כאילו 1 ושלישי ו11 נגיד,
בסדר, נראה פה. לא, אבל כשהם קוראים איתם אז כן שהם יסכימו שיהיה עוד תרגול.
זהו.
למרות שנראה אם צריך. אני מסכים, זה בינך לבינם בעצם. בסדר, אני לא...
אני רוצה להגיד להם
אני לא רוצה את השיעור לבטל, אלא אם אין ברירה.
כן. בסדר, זה גם תרגול אחרי השיעור. אז נגיד שבכל מקרה מחר לא עושים, ואז נודיע להם אם יש, זה כאילו שאנחנו קוראים טנטטיבית לשלישי ו11, תרגול השלמה ועוד לא בטוח שזה.
לא, אני לא אחרי. בינך לבינם התרגול. תרגול השלמה.
כן.
כרגע ראינו שיהיה תרגול השלמה.
יהיה.
שלא.
אוקיי, אז בשלישי יהיה תרגול. בשבוע הבא יש 2, בשלישי ו11 ורביעי.
אם אנשים מעוניינים, לא, אז נחליט בינתיים שאלה יש אותה אחרת. טוב.
לא יודעים מה. יכול להיות פעמיים בשבוע יש תרגול. מה? פעמיים בשבוע. נורא מבלבל. וואי, בדיוק. בפגישה שלנו בגיא, בעבודה. So we will do the PA next week in the time of the extra PA in the Tuesday 11 o'clock for the lesson. So next week we'll have two PA sessions, one in Tuesday 11 and the other one in the regular hours.
It's canceled 100%
Yeah.
for tomorrow?
Yeah. But the lesson, no. It depends by the
So
university.
it's just, I mean, I don't mind, but we would need to find an alternative time, and it seems a bit difficult. So what I suggest is to decide that we will have the lesson, and I mean, of course, there is some likelihood that lesson will be cancelled. It depends on the snow in the morning. When it starts to snow, so the weather forecast. So we'll see. But for now, the plan is to have the lesson at 12. And I would even suggest that if everything changes, because it's a bit unpredictable, if the weather forecast changes and it's not supposed to snow until the evening, then maybe it's better to have a PA session. But you should decide on this later. Okay. Where were we? Okay. So first of all, based on some questions that I received in the break, I'd like to clarify the notation, because I realized I was asked why I had the y0 there, and it was because initially I tried to make the notation more explicit, but decided not to do it, and I realized it might be a bit confusing. So this is what was written previously. So y, what I mean by y is the output of my network. So my network has a particular structure. It's a linear network. All it can do is combine, sum up the inputs linearly, okay, with some weights. So y is this. What I want, what I wish, but what I wish is to learn some function f of x, which might be a nonlinear function, okay? So I want the y's to be similar to f of x, and actually I should write here equal approximately, because in general, of course, if f is a nonlinear function of x, I cannot find a weight such that this will be an equality for all x's, okay? So this is my goal. There is some nonlinear function. This is f of x. This is what I'm trying to learn. This function exists. Okay? It exists. This is what I'm trying to learn. And I'm shown what we are shown when we are trying to adjust the weights are some examples. The examples of x, I actually should have written this. This is also important. The examples of x are drawn IID from some distribution P of x. Okay, so why? Because what I'm trying to understand is what can a neural network do? And I'm starting by discussing the most simple neural network that I can think of, which is one neuron that sums up its inputs linearly. The point is that a neural network is constrained. It can't do everything. It has some mechanistic structure. There are some mechanistic aspects of what it can do that affects what are the kind of computations that it can do. So I want to ask something about how well can I learn a function f if all I can do is generate some linear sum of the inputs. Okay, that's the main rationale. Okay, so and
Through y is this linear function?
so y again. When I write y, I mean this linear function.
This is the true observation?
No, this x is the observation. Y is what my network generates. What I wish is to find weights such that y will approximate the function f of x. Okay, and how am I generating this optimization over w? How am I adjusting w? I'm shown some examples, which I call x mu. I'm shown
for each one of these x mu's, I'm told what is f of x mu, and I denote this by y mu. So this is, I think, a bit the confusing part of the notation, because here y means the true f. Y mu is the true f for x mu, and what I want is that y will be y of x mu will. So my goal is that y of x mu will be approximately equal to y mu for each one of the examples. More specifically, to make this, to quantify this, I require that the square error between y of x mu and the true f of x mu will be as small as possible. Now, what I also mentioned right now, I'll repeat it, is that I've told you I'm shown some examples. What do I mean by I'm shown examples? How do I choose the examples? So the assumption is that x is drawn from some distribution p of x. And the distribution of p of x is important. It will be important for how well we can do. For example, suppose that the p of x is such that x is always the same thing. We could imagine that p of x is a very sharp distribution in the space of all possible x's, and actually always, whenever we draw an x, we always get the same answer. Then, of course, we can construct a network that will generate the correct answer. We just need to adjust one number.
So we have that
But
for any p that we want.
so the problem is different for every p, but we assume that p is known, the distribution p of x is known. I mean, when we
The function will be the same for every p, or
no, it will. First of all, since what we're doing right now is optimizing the w's for the example, from the examples, the w's that we will end up with will depend on the particular realizations of the examples that we've shown. I will. No. The function f is just some function of x. Yes, and we assume that there is some distribution of the x's. Okay. Okay, so what we've done so far is that write down, given the examples that we have seen, what does it mean? What will be the error as a function of w? And I will want to minimize this error. But before I do this, before I minimize it, I want to discuss a little bit this matrix, which I have written here, the correlation matrix of the inputs. So I claim that the matrix C training, this matrix is symmetric. Okay, this is easy to see. If I replace the index I and j, I get the same answer. Right? Because I can just replace the order of these terms. And I also claim that the matrix C training is positive definite. And let me show you why. So what does it mean that the matrix is positive definite? It means that if I construct this sandwich of this form, I take some vector u, and I take the matrix, and I multiply it by the vector from the right side. So this is a scalar, right? This is a sum over I and j, u, I, c, training ij, uj. This needs to be positive. If it's strictly positive negative, it should be positive. Okay, for all u. This is what I need to check. Okay, so let's write down what this is. So u transpose c u is equal to this thing, and now I will plug in the expression for c. So it's 1 over p, sum over I and j, sum over mu, ui xi mu, xj mu, uj. And this is equal to 1 over p. Now I will change the order of the summation. I will start by summing over mu. And this is a sum over I and j, ui xi mu. And I'm putting here the parentheses just in order to make a point. They're not, I didn't do anything by adding them. Okay? But now you can see that this thing, this sum, is really the sum over I, ui xi mu squared. Right?
When you find u, is it a vector of all zeros and only one?
No. So u is any u. If this matrix is positive definite, this should be positive for any choice of u, and vice versa. If this is positive for any choice of u, this matrix is positive definite. Of course, not any u except for the null vector. For the null vector, this will be 0. Okay. So in fact, you will see now that my statement needs to be a little bit refined. So what we got is that u transpose c training u is equal to 1 over p sum u transpose x mu or sum over mu squared. And now because there was a sum over mu in C. There was a sum here, and then I wrote it down here.
Why is it sum?
Ah, thank you. Okay, so now what I'm asking, what does it mean if I can find a vector u such that this is 0? If I can find a vector u such that this is 0, it means that u is orthogonal to all of the x mu's. Well, this is certainly larger or equal to 0. Okay, this depends on what we mean: strictly positive, negative, positive definite, or just positive definite. Right? The question is whether this is can be an equality sign. I want to discuss actually when it is strictly positive. Okay? So let me ask, when is this 0? For which u when can I find a u such that this is 0? I can find a u such that this is 0 if I can find a u which is orthogonal to all the x mu's, right? Because I need all these terms in this sum need to be 0. They're all non-negative. So I need all of them to be 0 in order for this to be 0. So this is 0 only if if I can find a vector u which is orthogonal to x mu for all mu. Now, the situation is as follows. If p is larger than n, okay, then I have here the number of vectors that I would need u to be orthogonal to is larger than the dimensionality of u. So think of 3 dimensions. So suppose that u is 3-dimensional, and I need u to find a vector u which is orthogonal to 5 to 10 vectors. Usually I will not find such a vector. I will find such a vector only if the x mu's are linearly related to each other, and this is something with measure 0 in the probability space of X mu's. X mu's are drawn from some distribution. The chance that the X mu's will be linearly related to each other is 0. Why? Because we assume that X mu is drawn IID from some smooth distribution. The cases in which they will end up being parallel to each other or linearly related to each other, it just has a probability 0. Yes, I will not show it, but it can be shown. Okay, so I will ignore it. It can happen, but it has a measure 0 as a probability. Okay, so I will assume that it doesn't happen. Okay, the chance that it will happen, that it will be precisely related to each other, such that they will span a space smaller than n dimensions, is 0. Okay, so if P is larger than n, then with chance 1, there is no such vector. And therefore, the matrix C will be strictly positive definite. C is strictly positive definite. On the other hand, if P is smaller than n, then of course I have here P vectors smaller than the dimensionality of n, so there will always be n minus P independent vectors for which U, C, U is equal to 0. So in that case, C is not strictly positive definite. There are some directions in which it's flat. Now, so you see here that we already can expect a fundamental difference between these two situations, and it kind of makes sense. This is an example where I have more examples than the number of parameters, because n is the number of weights. So this is a case where I have more examples than the number of parameters. And this is a case where I have a smaller number of requirements from my network, a smaller number of examples than the number of parameters. And so you will see that these two cases will behave very differently in terms of what my network can or cannot do. Okay. So let's start by talking about the case that P is larger than n. Actually larger or equal. So what does this, so just to clarify, what does this mean that the matrix is positive definite? Suppose that this was one-dimensional. C was 1 by 1 matrix, so P and N were 1. What does U, so U is one-dimensional, C is one-dimensional. What does U, C transpose U look like? Okay, so actually what I want to plot here is E training as a function of W. So just for the sake of the example, in this case, if W is one-dimensional, there is just one input and one output. You have to look back at your notes. There's an expression for E training, which is, it has a quadratic term, right? WC training W plus a linear term plus a constant term. How does this function look like as a function of W? Parabola. And this parabola has positive curvature or negative curvature? It's positive curvature because this matrix, which is now a scalar, is positive. Okay? So it will be some function like this. More generally, so this is one dimension. And now we look at the case of n dimensions. Because the matrix C is positive definite, if I will explain in a moment. Here it's W and this is E training. So now imagine I can only plot something in a two-dimensional function. I don't know how to plot a higher dimensional function. So this is an analogy to n dimensions, but so this axis will still be E training, and these two axes will be two of the weights of W. So I will get some function that looks like this, okay? But you have to imagine that it's really n-dimensional. The important point is that it has positive curvature in all directions because the matrix C is positive definite. So a general quadratic function always has just one minimum or one maximum, or if it has in some directions it has positive curvature, in other it has negative curvature, it has one extremum. Okay, but it always has one extremum, and in the case where the quadratic form is positive definite, it's a minimum. Okay, so there's positive curvature in all directions. And there will be some minimum, and this minimum is what we're after. We're looking for that minimum. Okay, let's write down what are the requirements from the minimum. So remember that we wrote that E training, this is the function that I'm plotting here, is half W transpose C training W minus U transpose W plus A. This was the error. And I want to minimize this with respect to the weights. So what will I get? From here, I will get, if I take the Wi appears here in two places, on this side and on this side. If I take the derivative with respect to this one, I'll get W transpose C training. But I need to take also the derivative with respect to Wi that appears here, and this will give me half C transpose W. And, I should put here an I. And this is an I too. Okay. So this is what I'm getting from taking the derivative here. I'm doing it a little bit fast. If you're not sure about that it's correct, do it carefully on your later on. Here, the derivative with respect to Wi will be the ith element of U of the vector U. And this does not depend on W, so this gives me 0. Now, these two terms are actually the same because the matrix C is symmetric. Okay? Because the matrix C is symmetric, the transpose of this is this. So actually what I'm getting here is C transpose W minus U, the ith element, and I want this to be 0. And therefore, I'll do it here. In vector notation, my optimal W, let's call it W star, is equal to the inverse of the matrix C training multiplied by the vector U. Here, I should add just to keep my notation the same, I had TR standing for training also on U. Okay. Okay, so this is when P is larger than N, this is the recipe for how to find the best W. And you might note that there is a very clear similarity between the equations that I'm getting here and the equations that I discussed in the beginning of the previous hour when I discussed an optimal estimator, an optimal linear estimator. Okay, and this is not a chance. This is not happening by chance. It's happening because we're considering a network which has the same structure, a linear network, and quantifying its performance using a quadratic expression, using a square error. But there are some important differences between what we did in the previous hour and what I'm doing now. Some of these differences are technical, and some of these differences are more conceptual or fundamental. So let me first just mention a few technical details. These are less important, but just when you compare the results. One difference is that here in the matrix C, which I've already erased, and in the vector U, these were correlation matrices, whereas in the previous hour, this was a covariance matrix. And the reason is simply that when I discussed the linear estimator, I included in the output of the network a possibility for a bias term B. Here I didn't include it. I could have included it. If I would have included it, if I assumed that the output of my network is W times the vector input plus some bias, the matrices here would be replaced by covariances and not correlations. So this is a technical point. Conceptually, in the first hour, we discussed an estimation problem, where now we're discussing a function approximation problem. So what does it mean, estimation problem? I have some observations that depend probabilistically on some theta, and I want to estimate theta based on the observations. Here, it's something else. I have some function of the inputs, and I want to approximate this function. But we can see why the problems are similar. Consider the estimation problem, and just consider hypothetically a situation where the inputs are deterministic functions of the theta. So we discussed a probabilistic situation. The inputs, the observations depend probabilistically on theta. But imagine a case where the observations are deterministically dependent on the parameter theta. We want to estimate theta based on the inputs. Basically, we're trying to learn some function of the inputs. We're trying to learn the correct relationship between the inputs and the theta. So in the specific case of the linear estimator problem, where the observations are independent of theta, they're deterministically determined from theta, we're really trying to solve a function approximation problem. The other very important conceptual differences between what we've done in the previous hour and what we're doing now is that now we're discussing learning from examples. We're not trying right now to optimize the response of the network, the approximation of the network to any x. In principle, that's what we want to do, but what we're trying to do is to do it based on a finite number of examples. And that's also why the covariance, the correlation matrices, C training and U training, if you look at their structure, they're not truly for example, C training is not the true correlation matrix of the inputs. It's the empirical correlation matrix of the inputs based on the examples that we've seen. Okay. So these are some comments about just the structure of this form and the fact that it's similar to what you've seen in the previous hour in the estimation problem. Anyway, this is what happens when P is larger than N. But now I want to discuss the case where P is smaller than N. So again, when P is larger than N, we have a larger number of examples than the number of parameters that we can adjust. When P is smaller than N, we have a smaller number of parameters, a smaller number of examples or requirements than the number of parameters that we can adjust. But if we try to follow the path that we took here, we encounter a problem. We need to inverse the matrix CTR, but remember that in this case, CTR has some flat directions. It's not positive definite. It's not strictly positive definite. And this immediately implies that it's not invertible. Okay? This means that what I've written here is meaningless. I cannot write down an inverse for the matrix CTR. However, this does not mean that we cannot solve a problem. In fact, the opposite is true. As I'll argue now, not only can we solve the problem, we can solve it with perfect agreement between the output of the network and the desired outputs. We can achieve zero error on all examples. And in fact, I will not do it right now. This we will do in the TA session. But basically, instead of trying to minimize the training error, the easier way to go about the problem is to just try to solve the equations. We try to solve the equations. Y mu is equal to W transpose X mu, where mu goes from 1 to P. Linear in the W. These are the variables that we need to solve for. Now, you can see here that we have n parameters, n variables. Sorry, it's a small n. And the number of variables is smaller than the number of equations. Is larger than the number of equations. We have a smaller number of equations than the variables. And as you'll see in the TA session, you can solve the equation. Not only can you solve the equation, usually you have, in this case, P is smaller than n. This should have been a small n. There's an infinite number of solutions. Turns out that there's an infinite number of solutions. I'll write them down. You will derive this in the TA session. There are many different ways I can choose the weights such that all these equations will be fulfilled. And so we say that the problem is under constrained. Or that there is degeneracy in the solutions. There are many different choices for the weights that will all give me zero error.
Does this hold for without any assumption of the examples?
Yes. Yes. I will write down to you what is the solution. Okay? But you will derive this. I'm not deriving it. I'm just writing down the solution. So the solution here. Okay, sorry for my handwriting. Under constrained. Under constrained problem. Or we say that there is degeneracy in the solutions. Okay, so here's how the solution looks like. And you will show it in the TA session. Turns out that the optimal weights can be written as a linear combination of the vectors, the examples vectors, okay, with some weights that I need to tell you what they are, okay. These are I call them omega mu. And we can add to this solution any vector that obeys W that is orthogonal to all the examples. Okay, from U going from 1 to P. This is the degeneracy. Okay, my ability to add to the W's any vector that obeys these equations, and because P is smaller than n, there's going to be an n minus P dimensional space of vectors of this form, and I can choose any vector of this form, and and you can see from these equations why I can do it. Because if I just plug in this equation, look at W transpose multiplied by this W star. So there will be some contribution from this, but this vector, by definition, is orthogonal to all the U's, so it will not change the Y mu's. Okay, so because there are vectors, so any vector that obeys these equations necessarily does not affect the output of the network on the examples. Okay, so this is the source of the degeneracy. And now, since I have here, okay, now I need to tell you what are the omega mu's. And the omega mu's turn out to be equal to the sum of, to the following expression. Where, okay, so this, if you want, this is a product of a matrix, of a P by P matrix with the vector of desired outputs. And this matrix is the inverse of a matrix that I will write down here. It's a P by P matrix. Q mu nu is a P by P matrix whose mu nu element is X mu transpose multiplied by X nu. So remember, the X's are n-dimensional vectors. So for any given mu and nu, I have here an n-dimensional vector, scalar product with another n-dimensional.
Or just move the board.
This is a simple trick. Okay, so for any mu and nu, this is an n-dimensional vector, this is an n-dimensional vector. I take the scalar product and I get a number. So this is the matrix Q mu nu. In this, as a P by P dimensional, as a P by P matrix, this matrix can be shown to be positive negative, is positive definite, and therefore it has an inverse. Okay, and therefore these equations can be solved. Now, just note, it's kind of mathematically, it's kind of interesting to note the similarity or duality between the form of the solution that we found when n is larger than P and when n is smaller than P. When n is larger than P, we write the solution in terms of this matrix Q, whose elements Q mu nu can be written as sum over I x I mu x I nu. And this is a P by P matrix. And again, when n is larger than P, this solution achieves zero error. Okay? When n is smaller than P, the solution was written in terms of another matrix, which I called C training, and it was a n by n matrix. And the jth element of it was 1 over P sum xi mu xj mu. So here the sum is over mu for different i's. Here the sum is over I for different mu's. So mathematically the form is very different in two different spaces. One is the neural response space and one is the example space. Okay, this is a mathematical curiosity or similarity. And I think that I will need to end now. Okay, so let me just wrap up what we've seen today, and we'll continue the discussion hopefully tomorrow. We've seen that when the number of examples is smaller than the number of weights, we can simply find a network that achieves the desired output for all the examples. Okay? In fact, there's degeneracy. There are many different choices of the weights that will achieve this result. And when when p is larger than n, the number of examples is larger than n, then typically, I didn't show this, but typically we will not be able to achieve zero error, but we can minimize the error, and we saw what is the choice of the weights that achieves the minimum error. Okay. Yes.
The fact that we can get zero error doesn't mean anything about getting close to the real error, right?
Exactly. So this is what we'll discuss tomorrow. The fact that, in some sense, it tells me that it's not even interesting that the